So the idea here is, again, like we kind of want to think about like, why do we need to use a definite integral to do these problems? Okay. So before we talk about that, let's see how do we define fluid force first, and then we'll kind of see why do we need a definite integral to think about these kinds of things. So before we talk about force, we need to think about what is the scientific the physics definition of pressure, and this is it. That's a Greek letter right there. That's rho. The Greek letter rho. It's not a P. It stands for density, volume density. G is gravity, D is depth. Okay, so that's kind of what we've got going here. All right, so let's just see kind of what pressure. I mean, we all kind of have a besides like the pressure of taking a math test, but the physics definition of pressure. What are we talking about here? I think we all have an intuitive idea of what that is, right? Like if you go swimming, you know what pressure is, right? The deeper you go, like if this is the surface of the water, right? And you go down below the surface of the water, you know that the deeper that you go, the more pressure that you feel in your ears, right? And so you can see what makes that happen according to this formula. Well, two of these things are fixed, right? That's the density. That doesn't change, right? Density of water stays the same, right, for the most part anyway. So that's a constant. G, that's also a constant. That's just gravity. So that neither of these two things change. So the only thing that causes the pressure to go up is what? That's it, the depth. So this is the thing that's the variable there. Everybody see what I'm saying there? And that kind of makes sense, right? The deeper that you go, the bigger that D value goes, both of those other things being constant, the bigger that's going to get too, right? So D gets bigger, P gets bigger. In fact, in a linear fashion right there, right? Because P and G, or rho and G are both constants. Okay, so that's the definition of pressure. So now pressure itself then can also exert a force on an object if there's an area, a surface area to push on, okay? So the definition of fluid force in this case, force in general, fluid force, what's that? That's just, and you can see right there, it's pressure times area, pressure times area. So now that we know what pressure is, then we can say, okay, well, how do we figure out the force being exerted on a surface? Well, if you know what the pressure is and you know what the area of the surface is, then you can figure out what the force is, okay? So now under what circumstances might we care about this? Like suppose that you're building some kind of submersible, right, in the water. Well, what you're going to definitely want to know what force is being exerted, particularly like on your windows, right? If you have windows in this submersible craft, suppose you have a window in that thing, right? And then the surface of the water is up here. And you want to know what is the force being exerted on that window. Well, what are the two things that you need to know in order to answer that question? You need to know the pressure, right? And that depends again on the depth, D. So the lower you go, the bigger that quantity is going to be. And then the other thing that matters is the area of this thing, right? What's the surface area of that window? The bigger the area of the window, the more force that's going to be on it, right? And so what's actually happening? Well, on one side of the window, you've got just air, where you want to be inside the submersible. On the other side, what do you have? You've got all this water pushing on that window. It's a pressure times an area, right? The pressure of the water times the area of the window. That's exerting a force on that window. And the question is, what is that force going to be? So that's what we're trying to find out here. All right, so a circular window is probably not the best thing to motivate this. So I'm going to just redo this with a square or rectangular shaped window instead. It's just easier to think about. So suppose this is the water surface, and then maybe you have this rectangular window down here underwater. Okay. And the next question is, why would we need calculus to figure out the total force being applied to this window? Well, if you think about it, at the bottom of the window, so say down here, what's going to be different than at, say, the top of the window? Well, the bottom of the window is deeper, right? And so what's happening down at the bottom of that window? Well, the pressure is bigger, right? The pressure is more at the bottom than it is at the top. And since the pressure is greater, that means the force is greater too, right? So the force at the bottom of the window is different than the force really at any other height on the window. You see that? So what we have to do here to figure this out, the total force that would be applied to this window underwater would be to think about, well, let's sort of look at a single strip of the window, right? Maybe you can get the idea. We've been doing this kind of a lot. We're almost out of time here, but I think I can get through this. And you would look at a little strip. You could say that that strip has width delta y. It's going to have a length associated with it as well, right? A length. And in fact, I'm going to go ahead and call that thing L of y because it could potentially change according to y. So let's think about what is the force being exerted on that strip, right? What is the force that's being exerted on that strip? Well, it's the pressure, right? The pressure times the area, right? But the pressure we said was rho times gravity times the depth. So we would have to say, well, what depth is this thing at? And for the purposes of what we're going to do here, I'm going to call the surface of the water y equals 0. And I'm going to say that going down is actually increasing y. Because when we use that letter D for depth, that really kind of means that we're pointing downward for the positive direction. So let's just stick with that convention. It also negates the use of a lot of negative signs. And so basically what that means is that this strip is at some height or depth really below the water's surface, right? We'll call it y sub I. Okay, so that means this thing is at some depth. Call it y sub I. And then the area, what's the area? Well, the area is just going to be the length of that thing, the length, times the height, which we call delta y. Okay, so there it is. That is the formula then. Well, close to the formula, but we can get the formula from here. So that's the force just on one strip, and then you can imagine again, like what else would we want to think about? Well, what's the force on another strip that's below that, like down here, right? And what's the force on the strip that's just slightly above it, right? And then what would we do? When we take all the forces of all of these little strips, add them all up, and then what do we get? Well, we get the total force being exerted on the window. So you can kind of see where the calculus is coming in here because we have to sum up all of these forces, right? So you would get like an approximate force, and that would give you the summation of all this stuff, rho and g and y sub I, and the L of y sub I. Yeah, have to be y sub I there, and then delta y, and then we can take this from I equal 1 to n, and so on and so on. And then eventually you get to the limit of this, and then so eventually that limit turns into the exact value. And so what do we get for the exact value? We get rho g integral from a to b. Now they call this thing h of y, but I have not found one where it's anything other than y, so I'm just going to put a y there, and then the L of y. And then the delta y turns into a dy. So there we go. That is the formula for the force on some that basically has like water behind it or water pushing on it or some kind of other fluid that's pushing on it. It's called fluid force, okay? And so where might we care about this kind of thing? Well, certainly somebody who's building a submarine would care. Somebody who's building a dam would certainly care about this, right? Because if you don't build your dam strong enough to withstand the force of the water on the other side, you're going to have big problems, right? So you definitely want to know what is the force that's being pushed on a large body of water that's being held up by some kind of structure, right? So this is super important, right? If you're going to become a civil engineer or something like that, you're definitely going to be very interested in this, right? So I think last time we did just talk about like why we need an integral for this and what the setup is for finding fluid force, like on a surface that has some kind of fluid behind it, usually water, but sometimes not. And so just to remind us, the formula for that was if you want to find the fluid force on a surface, it's written there on your worksheet, but I'll just write it up here too. So rho g times the integral from c to d. h of y, L of y, dy. And just remember what I said last time. The convention that I use for these types of problems is that I always set the y equals 0, the x-axis that is, at the surface of the water, and then we count that if you go downward, that's actually increasing y values. So it's just it's a convention that allows us to kind of avoid a lot of negatives in the problem. As long as you just stick with that convention, this is always going to be the case, that h of y is going to be y. Okay, I think it's just, that's another reason that it kind of makes it easier to kind of stick with. And I'll show you what I mean in these examples here. So take a look at example 1, and again, I'm on the worksheet for 8.3. Everybody have that? If anybody needs it, I can share it up here too. Okay, I'll just assume everybody's got it. All right, so it says the tank is in the shape of a rectangle with height 5 feet and width 4 feet. Find the fluid force on one side of the tank. Okay, so in this case, we've got a rectangular tank. That's about the easiest type for this type of problem that we can hope for. It's kind of like with work type problems where we had a conical shaped tank versus like a cylindrical shaped tank. It's kind of like the difference there. If it's rectangular here, things are pretty simple. So we're assuming that this tank is full of, let's just say water. It doesn't say what's actually in it, but let's just say water. And it says feet. So for water, rho is equal to 62.4 feet, or sorry, pounds per cubic foot. That's the density of water in the English system. In the metric system, it's 1,000 kilograms per cubic meter. Okay. Usually, I should have put that in the problem, but I didn't put it here. Anyway, I'm giving it to you now so we know. Okay, so what I was saying before is, we'll just assume that this tank is full of the water. We'll call this y equals 0 at the top of the tank. Again, that's a little bit different than the way we had been doing. For example, those work problems, we put y equals 0 at the bottom of the tank or container, whatever it was. Here we're doing a little bit differently. And I think you'll see why in a second here. And then remember what we wanted to do, what we've been doing with a lot of these, application type problems, we always kind of see what's happening with a small segment of the whatever it is that we're looking at. And we're going to do the same thing here. We're going to look at a little strip of the tank. And that strip will have height delta y. We know that this tank has, it's 5 feet high and its width is 4 feet. So we'll go ahead and label that too. Yeah, we want to make that sort of convention that y equals 0 is the top of the tank or whatever, or wherever the liquid ends. This rho here, that's the density of water in the English system. What I was saying up here is that in the metric system, you have to put this rho g. You have to include gravity. But in the English system, you don't, just like when we were talking about work. And so in the English system, they use this W letter to stand for weight density, and that's just replaces both of the rho g combination there, okay? The L of y in this case is just the width of the strip that we have here, this strip here, right? And in this case, what I was saying that this problem is maybe one of the easier ones is because that L of y is a constant, right? Just 4. It doesn't, in other words, that the length of that strip that you're looking at doesn't depend on your height or your depth, I guess, in this case. Okay, and then so basically for this problem, it's pretty simple. H of y is just y, as I was trying to say, that's pretty much always the convention if you go by what I've been saying, where y equals 0 is at the top. If you do that, then h of y is always just y. Okay, then for the bounds of the integral, we're going to start at 0. Again, remember that y equals 0 is actually the top, and then we say that increasing y is this way. And so we're actually integrating from the top of the whatever it is down to the bottom of it, where the top is actually the lower bound and the bottom is actually the upper bound. And so that means that we're going to integrate from 0 to 5. Okay? And then plugging it into this formula here, h of y, L of y, well, we just said h of y is just y. Right? H of y is just y, so that means we put y there. L of y in this case, we said was this, just constantly 4. And so see that in this particular case, we get a very simple integral for this. Just 4y, in fact, that's it. And so you can even include that 4 then. You could put it out in front with the other constant there. 249.6, so this is the integral that we have to do. 249.6, integral from 0 to 5, y dy. Okay, so this one's the integral that we actually get here. Again, really simple. And then we'll take our antiderivative, 1/2 y squared, plug in 0 and 5. So that's 25 over 2, I guess, 25 over 2. And I'll multiply that by the 249.6, 3120. And remember that this is the English system here, so we're looking for fluid force here, fluid force. And so what is the measure of force in the English system? Measure of force is pounds, exactly. So this is just 3120 pounds. And that, I mean, that really, I think, tells you like what we're actually dealing with. That's a lot of weight, right? 3,120 pounds. That's a lot, right? It's a lot of weight. This tank is only 5 feet tall and wide. So basically, if this was like a big fish tank or something like that, maybe an aquarium fish tank, you would want to make sure that that wall of glass, is strong enough to withstand 3,120 pounds of force, right? And if you didn't do that, you'd have big problems, right? This thing would break open. Okay, let's try one where L of y is not just a constant. And this, there's not really too many questions I can ask about this. In fact, this is pretty much it. How much force is being exerted on some kind of side of a tank or perhaps a dam. So what I'm going to probably do on the test is you're not going to get one as simple as number 1. It'll probably be more like number 2 here, where the L of y is something that you have to figure out. It's going to be a function of y. So let's go ahead and draw a picture of this situation. So we've got sort of a trapezoidal shaped dam. I'm remembering from last semester that I was supposed to fix something there. I think I said rectangular shape when it should have been a trapezoid. Yeah, I think I fixed it. It was example 2, I think. You used to say rectangular, but it's clearly not a rectangle. It's a trapezoid. Okay, so there's the shape of it. Height is 100 feet. Let's just go ahead and label everything. All right, so there's the strip that we're going to be looking at. Again, this should be getting familiar now, where we examine what's happening to a small segment of the situation. So that's the L of y. And then we call this y equals 0 at the top. We say that this is going to be our increasing y. And then just go from there. All right, so that's the drawing of the situation. So in this case, this is still the metric. Sorry, this is not the metric system. Still, only the one problem you guys are going to do is metric. This one is still English. The force here, just plugging everything in, is going to be the weight density in this case. Again, we'll just assume it's water, so 62.4 pounds. Well, actually, I don't need to write the units on that. 62.4. Integral is going to be from 0 to 100. Again, with the convention that we're doing here, h of y is just y. And then L of y is here in this case. Now, in this case, the L of y is not a constant, so we'll think about what that is in right now. What is L of y? It's definitely not a constant function, but if you look at the picture here, it is a linear function because these, again, the sides are straight. This sort of had curved sides, then it wouldn't be a linear function, but they do, so linear function. And so what we know about L of y is that it has to have the form of a linear function. It has to look like my plus b. And again, this might remind you of the way that we were figuring out what the when we had that conical shaped tank when we were doing work, we did something kind of similar to this. What do we know about this L of y? Well, right now we know two things about it. We know what L of 0 is. We also know what L of 100 is. What's L of 0? 90, exactly. And what's L of 100 is then 70, exactly. Okay, so if you remember what I was saying about slope, we kind of got to get out of the idea, the old ways of thinking about slope as just being change in y over change in x. Really what it is the change in the dependent variable divided by the change in the independent variable. And again, the best way to kind of think about that is to look at the values over here. That's going to be the values for the dependent variable, and then these are the values for the independent variable. And so for this problem, m is going to be equal to 90 minus 70 over 0 minus 100. So 90 minus 70 is minus 20, and then, sorry, positive 20. I'm putting the minus too soon. It's positive 20, and then the denominator is negative 100. So that ends up being negative 2 fifths. No, 2 tenths, I guess, which is 1/5, right? And then also, if you remember about linear functions, if you know what L of 0 or whatever the variable is, if you know what f of 0 is, then that itself is the b value here. That is the b value, okay? So we don't even have to do any work for that. So that's telling us that our linear function in this case must be negative 1/5 y plus 90. And then just, you can always check this too, just like we did with the work problems. Does this produce the values that we expect, right? Like if you plug in 0 for y, what you get 90, right? And so that thing really does give you the value when y is 0. And then when you plug in 100, then 100 times 1/5, that's 20. That'll be negative 20 plus the 90. That gives you 70, right? So that's the L value at the bottom of the dam. Okay, so everybody see how we got the linear function out of that? In fact, really, that's probably one of the maybe the hardest parts about this is just to figure out what that L of y is going to be. Once you know what that is, then the rest of it is just plugging stuff in. So just put the y there, put the L of y now that we know what it is. And there's our integral that we actually have to do. So not going to get difficult integrals on these problems. The integrals themselves should be pretty simple. Okay, so antiderivative, we're going to have to raise that to the third power, so we'll divide by 3. We're going to get 1/15 y to the third. We're going to have to raise that y to the second power, so we have to divide by 2. That gives us 45 y squared, and plug in 0, plug in 100. So what is that? That's 23 million, right? A lot. 23 million pounds of force. Okay, so everybody, again, that is a lot, right? Almost 24 million pounds for a 100-foot dam that's got this shape. Definitely a lot. So here's a sort of conceptual question for us. That picture that I drew of the dam at the top, the trapezoid shape, that's just like looking at the dam straight on. Suppose that you had a dam, that you're looking at from the side, perhaps, like something like this, and the water is here, right? Here's the water, and the dam is holding back the water. Does it matter how far back this water goes? Like if I have maybe a huge lake over here, right? Does it matter if I have a gigantic lake behind this thing and a whole bunch of water, or versus maybe a situation like this? Maybe I have a dam like this, and I only have a tiny little bit of water. So suppose I have a wall right here, and I just have a little bit of water right here. Right? Does it make a difference? Like suppose these dams are identical in every other way. Does it make a difference the force that's being pushed on this dam versus the force that's being pushed on that dam? Only the density matters. That's it. Only the density and the gravity matter. That's it. So no, that's the answer, right? You're correct about that. It doesn't matter whether you have a 100-mile lake behind that dam or you have even just a strip of 1 inch of water behind it. only thing that matters is the density and the depth, really, right? How deep is the water, right? So basically, it's kind of a weird thing, right? Like if you only have 1 inch of water behind that thing, but it's that deep compared to a 100-mile lake behind it, the force being exerted on the dam is exactly the same. Kind of interesting that way. Does that make sense what I'm saying there? Okay, yeah, it's a counterintuitive sort of property of physics, but yeah, it is true. All that matters is the depth of the water and or the depth of the fluid and the density of the fluid. All right, so with that in mind, I think that ends that problem. So yeah, for this problem that you're going to work on now, I'll give you a few minutes to do that. But just to kind of set it up for you, this is an equilateral triangle. This is going to be a little bit harder also because you have to kind of figure out what the top bound of that integral is going to be. Because all they tell you here is that this is an equilateral triangle, right? 8 meters on each side. But what do you need to know to figure out the force here? Like, what is one of the quantities that you need to know? Well, you need to know the height of it, right? You need to know what that is. Because that height is the top bound of the integral, right? You don't have it here clearly, so you're going to have to figure it out. But I think you guys are, you've had enough math at this point to see that you've got a right triangle there, right? Like if you put that there, and since it's equilateral, you could see that this distance would be 4, and then you could just use that fact and the Pythagorean theorem to figure out what that h is. That then is going to be the top bound of your integral, okay? And that is also going to have something to do with your uh, the L of y that you have to find, right? Because the L of y is this distance here, right? L of y is the width of whatever strip that you happen to draw on there, right? You can see that that clearly changes as the height changes. Oops, I didn't draw that correctly. You do it like this. So suppose this is your strip. This distance is your L of y. And you're going to have to use, that h value there as well to figure out what that L of y is going to be. Okay? So with that in mind, I think Michael's camera is having some issues, but he sent me his solutions. So what I'm going to do is give you a few minutes to work on this, and then once you're done, I will. Well, actually, I'll just post them here in a few minutes. You can look at them as you want. I'm still going to take a little break here, turn off my camera and stuff, but I'll give you about 10 minutes to try to work this problem. Well, maybe less than that because it's probably not going to take that long. But think about it, try to figure it out, and I'll pop up the answer to this in a second here. All right, so I think Michael's doing this a little bit differently than I would have done it, but it's okay. Good to see it from 2 different perspectives, I think. Yeah, so let's see. Starting out, the first thing that he does here, right there, is to figure out what that height is. Remember, I was just mentioning that we need to figure out what the height is. That's this side. I guess you're treating that as the origin right there. I see what you're doing there.
Yeah.
And you're saying that this is a point on there, right? 4 root 3, right? Okay. Yeah. So yeah, that's fine. And then yeah, that means that the width here is 4, right? And then the this side is 8. And so you got the 4 squared plus the 8 squared equals the y squared, and so you get this for your h, or y. He's calling it y there. Remember, that's 16 times 3, so that becomes 4 root 3. So that's the top bound of the integral then. Okay? And then separately over here, what he's doing is he's actually trying to he's doing half a strip here, I think. That's what that is, right?
Yeah, it's half a strip.
Yeah, that's half a strip. Treating this as a point on, this is like the xy, this is the origin right here at the bottom, 0, 0. He's treating that as a point that's up there, and yeah, he's using half a strip basically. So with that in mind, m value there is going to be the change in this value, right? The change in that, which 4 root 3 minus 0, and then divide that by the change in the x value, which is 4 minus 0, and that gives a slope of root 3 there. And then very similarly here, I would have called that L, but that's X is what he's calling it there. So again, what I would have done here is I would have said that L of 0 is equal to the length at the top, which would have been 8, and then L of, what would it be, 4 root, wait, what do we say? Yeah, 4 root 3 would have been 0. And so I would have gone M is equal to 8 minus 0 over 0 minus 4 root 3, and I would have gotten a slope of 8 over 4, so that's negative 2 over root 3. Then the equation would have been L of y, so doesn't let me erase, L of y is equal to negative 2 over root 3 y. Wait, what are you doing for your h there, though? What's that h? 4 root 3 minus y?
So what I did with that one was, since I put the origin down at the vertex, the height that the water has got to go is from wherever the y value is up to the top of the triangle.
Oh, I see. Okay, yeah. So that's true. Now that's doing it in a way that such that the top of the tank is not y equals 0. Okay. Yeah, I'm gonna go ahead and do this my way as well, but I'm just gonna continue talking about the way you did it, just so you can see a different way. Yeah, this is a situation like what I was talking about. If you don't treat the top of the tank as y equals 0, then you have to make your h be something else. The h of y would not simply be y. So with the convention that I use, you kind of avoid that, having to figure out what that h of y actually is. Anyway, with that in mind, and then he's got his L value here. Notice that that's doubled from what it says right there. Why is it doubled? Because again, we said that we were only doing half of it right there. So he doubles it to make it the entire length there. Yeah, and then with the convention that he's got y equals 0 at the bottom, the h is different. But it all actually works out in the end. Like the integral that you get is doable, and then you get this answer at the end. I'm going to go ahead and just show this the way that I would do it with the y equals 0 at the top. So let me just share my screen on that one and go through it an alternative way. Again, either way is fine. In fact, the way that Michael's doing it there is the way the book does it. So if you're interested in seeing how the book does it, that's the way that it would have been done in the book. Okay, yeah. So the way I would approach this problem, finding that height is the same. Finding the height is exactly the same. This is 8. I'm sorry, that's what I would call y, or h actually. And then these sides are 8. And then, as we said before, since that's equilateral, this is going to be 4 here. So you could say h squared plus 4 squared is equal to 8 squared. Solving that, you do get h equals, what was it, root 48, which is 16 times 3, which is 4 root 3, right? And then the strip here, now that we know what that is, I'm just going to erase it. And then the strip here, you can just draw it anywhere. Call that L of y. My convention again, calling that y equals 0, increasing y right there. L of y is a linear function, so it's my plus b. M in this case is going to be the change in, well, actually, before we figure out m, we have to know that L of 0 is 8. L of 4 root 3, since that's the height, is going to be 0, because, again, at the bottom, there's no width, right? It's just the point of the triangle there. And so the slope of this thing is m is equal to 0 minus 8 over 4 root 3 minus 0. So the equation of this linear function is y equals negative 2 over root 3 y plus 0, again, because, or no, in my case, yeah, L of 0 is 8, so this one would actually be plus 8. Okay, and then you can check just to make sure that what we have here. Again, the differences here between what I'm doing and what Michael's doing is that he said y equals 0 was down at the bottom. And if you say y equals 0 is at the bottom of this thing, well then clearly y of 0 would actually be 0 there, right? If that's your convention. And that's why his b value was 0. My b value is not 0, since I'm saying that y equals 0 is at the top. But again, it all works out as long as you just stick with whatever convention you're using. Okay, so that's my L of y, and then for the force we would get 840. That's the density. We do need gravity on this, so we get 9.8. Integral here is going to be 0 to 4 root 3. That's the height of this thing. H of y in my case is just y, and you can see that's kind of the difference there. In mine, the linear function has that plus on the end of it. In Michael's, the h of y is the thing that's got something added to it. Again, simply because of the convention there. And then the L of y in our case here is this. And I'm assuming that if we do all this, we get the same answer, but let's just go through. I'm hoping we get the same answer. If we don't, that's a bad sign. Okay, so this is the integral that we have to do then. So that's 8232. Antiderivative there. We'll raise that to the third power, so we're going to get minus 2 over 3 root 3 y to the third. Plus, in that case, we have to raise it to the second power, so we're going to get 4y squared. Plug in 0, plug in 4 root 3. And I'm just going to assume that we're going to get the same thing so that we don't waste time on this, but plugging in that 4 root 3 should get the same answer that Michael got. And in this case, the units, force in the metric system, newtons. I guess we should probably just verify.
Yeah, never trust my arithmetic.
Yep, same answer, so that's a good sign.